Welcome to lecture 24. In this week, we are talking about single variable optimization methods. In our previous lecture, we have introduced two region elimination methods, namely dichotomous search method and interval halving method. You have noted that once a minimum is bracketed within an interval, then we need to evaluate functions at two different points within the interval, so that we can eliminate a part of the region. Now, once a part of the region is eliminated, one point may still be available within the interval. So, it will be advantageous to us if you can design a search algorithm which will make use of this point available from the previous iterative step. In that case, effectively we will be making one function evaluation at every iteration, of course, except for the first iteration. In this lecture, we will introduce another two region elimination methods, namely Fibonacci search method and golden section search method, which will make use of this property. So, let us start our discussion with Fibonacci search method. Fibonacci search method uses the sequence of Fibonacci numbers to reduce the interval of uncertainty. These numbers are defined as follows: f0, the first Fibonacci number, is equal to 1, f1, the second Fibonacci number, is also equal to 1, and then any number fn is the sum of the preceding two numbers. So, fn equal to fn minus 1 plus fn minus 2, where n is 2, 3, 4. So, if you follow this sequence, the first few Fibonacci numbers will be 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, and so on. So, first two Fibonacci numbers are 1, and the third number onwards you can compute it as sum of the preceding two Fibonacci numbers. The Fibonacci numbers are found in nature. Look at the figure. Fibonacci spiral found in both snail and she cells. Fibonacci numbers are also found in various flowers. Look at the figures. There are flowers with 3 petals, 5 petals, 13 petals, 21 petals. 3, 5, 13, 21 are all Fibonacci numbers. So, now let us see how this Fibonacci sequence can be used to constitute an optimization search algorithm. In case of Fibonacci search method, at each iteration the length of the interval is chosen according to Fibonacci numbers. When we require 2 points for region elimination, we know this. Once the minimum is bracketed, we need 2 points within the interval to eliminate a part of the region. In Fibonacci search method, out of these 2 points, one is always the previous point and the other point is new. Therefore, only one function evaluation is required at each iteration for Fibonacci search. Let us now explain with the help of this diagram. Let the initial interval is b minus a. We have assumed the minimum is bracketed between a and b. So, the initial length of interval is L equal to b minus a. At iteration k, two intermediate points are chosen such that each is L k star distance away from either end. So, x 1 is L k star distance away from A and x 2 is again L k star distance away from the right end B. Now, depending on the function values, a part of the region will be eliminated, either A x 1 or B x 2 will be eliminated. In either case, the remaining interval will be L k. This is also L k and this part is also L k. Now, if we define L k star as f n minus k plus 1 by f n plus 1 into L, where n is the total number of iterations that we will perform and k is the iteration counter. So, let us define L k star as f n minus k plus 1 by f n plus 1 into L and L k equal to f n minus k plus 2 by f n plus 1 into L. Then it can be shown that L k minus L k star is equal to L k plus 1 star. So, L k plus 1 star will be used in the k plus 1 iteration to place these points x 1 and x 2. Because of this, any one of these 2 points used in the iteration k will be retained as a point in the k plus 1 iteration. So, in the k plus 1 iteration, we have to make one function evaluations. So, here is the algorithm. We know that the minimum is bracketed in the interval a b, the length of the interval is b minus a. We have to define in the beginning the total number of iterations or function evaluations that we are going to make. So, n equal to, let the n equal to total number of iterations. We set the iteration counter equal to 2. Normally, we set the iteration counter k equal to 2 for Fibonacci search method, because the first two Fibonacci numbers are same and they are 1. So, next let us make use of our definition L k star, which is f n minus k plus 1 by f n plus 1 into L, to locate point x 1 and point x 2, which will be L k star distance away from either end. So, x is x 1 is a plus L k star and x 2 is b minus L k star. Now, evaluate the function at x 1 and at x 2, make use of the unimodality property of the function, and we will be able to eliminate either a x 1 or x 2 b. So, in this case, as the diagram shows, the function value at x 1 is higher than the function value at x 2. So, the minimum definitely will not lie in the region a to x 1. So, we will set new a and b as a will be set as x 1 and b will be set as b. So, again we find out the L k star in the next iteration, that means k plus 1 iteration. So, L k plus 1 star, and we will continue until the maximum number of iterations are reached. Let us learn few important points about Fibonacci search method. Fibonacci numbers have to be calculated and stored at the beginning of the algorithm. At every iteration, the proportion of the eliminated region is not the same. Number of iterations required need to be specified in advance. Fibonacci search algorithm is optimum in the sense that it gives the largest ratio of initial to final interval for a fixed number of function evaluations. After n function evaluations, the interval of uncertainty reduces to 2 into length of the interval divided by f n plus 1, where n is the total number of iterations to be performed. So, after n function evaluations, the interval of uncertainty reduces to 2 into b minus a divided by f n plus 1. Thus, for a desired accuracy delta, the number of function evaluations required can be computed from 2 by f n plus 1 into b minus a equal to delta. So, all you have to do is you set this value to delta. Delta is a specified small number which is the desired accuracy, and n is the total number of iterations required. So, from this expression it will be possible for us to find out n, the total number of iterations required to achieve the desired accuracy delta. Now, let us take an example to understand the working of Fibonacci search method. Let us consider the one dimensional function x square plus 30 by x, and we want to minimize this function in the interval x equal to 1 to 6. You can check that the minimum lies somewhere within 2 to 3. Note that it is not necessary to draw this figure, but if we plot the function, we will know about the behavior of the function. You will get an idea about the minimum point, and since we are talking about one dimensional functions, it is easy for us to plot the function, but for the working of the algorithm it is really not required. But of course, yes, you must know the interval within which the minimum lie as the initial interval. So, minimum must be bracketed at the start of the algorithm. So, let us see how it goes. In the first iteration, we set a equal to 1, b equal to 6, is a given interval. So, initial interval L is b minus a equal to 6 minus 1 into 5. Let us say that we will perform only 3 iterations. Note that for actual practice, we will set the n to a much higher value. So, let us set iteration counter k equal to 2. Now, let us find out L 2 star. So, that can be computed from f n minus k plus 1 divided by f n plus 1 into L, where n equal to 3 and k equal to 2. So, this gives us f 2 by f 4 into L. L is 5, f 2 is 2 and f 4 is 5. So, L 2 star is obtained as 2. So, x 1 is a plus L 2 star, which is 1 plus 2 is 3. X 2 will be b minus L 2 star, which is 6 minus 2 is 4. So, next step will be to evaluate the functions at x 1 and x 2 and eliminate a part of the region. So, now let us go to step 3 of iteration 1. You remember this was 3 and this was 4. So, evaluate the function at x 1 and x 2 and it becomes 19 at x 1 and 23.5 at x 2. So, f x 1 is less than f x 2. So, definitely we can eliminate the region x 2 b. The minimum cannot lie on the right hand side of x 2 because x 1 f of x 1 is less than f of x 2. So, now we will set a equal to 1 and b equal to 4. So, my interval from 1 to 6 now reduces to 1 to 4. So, first iteration is complete. Now, second iteration, we start with step 2 because the step 1 was those initialization. So, compute L 3 star, again put n equal to 3 and k equal to 3 in if f n minus k plus 1 by f n plus 1 into L, and you compute L 3 star as 1. So, x 1 is 1 plus 1 2 and x 2 is 3. A was 1, B was 4. Note that this point was also present in iteration 1. So, effectively we have to evaluate the function only at this point x 1 equal to 2. So, step 3 of iteration 2 will compute f of x 1, which is (19) and f of x 2 is also 19. So, we can eliminate both this part and set A equal to 2 and B equal to 3. So, second iteration is complete. So, minimum has been bracketed between 2 and 3. In actual practice, we should consider higher value of n and then you can proceed as shown. So, this is the working of the Fibonacci search method. Note that one point is always obtained from the previous iteration. So, next let us move to the golden section search method. So, golden section search method is another region elimination method which makes use of one point that is available from the previous iteration. Two numbers p and q are in a golden ratio if p by p plus q equal to q by p. We can write this as q by p equal to tau, then 1 by 1 plus tau equal to 1 by tau and tau square plus tau minus 1 equal to 0. If you solve this, you get the value of tau as 0.618 approximately. This number is known as golden ratio. Note that tau square plus tau minus 1 equal to 0 is a quadratic equation. You can solve it using the standard formula, and by solving it and taking only the positive value, you get 0.618. So, 0.618 is known as golden ratio. This golden ratio has been known for quite long. There are several architectures which have made use of this golden ratio. You can see in the figure the Parthenon in Athens, which is present in Greece. If you look at this rectangle, this is a golden rectangle, meaning the length and width ratio is 0.618. This is the famous picture Mona Lisa. Again, the rectangle shown is a golden rectangle. This is a regular pentagon. This length by this length will also be in golden ratio. Same here. It will be in the golden ratio. So, this was known for quite some time, and it has been used in several architecture and such figures, and it is known to have its aesthetic values. What is the relationship between Fibonacci numbers and golden ratio? The Fibonacci sequence we know fn equal to fn minus 1 plus fn minus 2, where n is 2 onwards. So, now if you take the ratio of consecutive numbers in the Fibonacci sequence, you see that this ratio converges to approximately 0.618, which is the golden ratio. So, as one proceeds, the ratio of consecutive numbers approaches the golden ratio. So, how this golden ratio is used to construct a search algorithm? Look at the figure. Let us say the minimum is bracketed between these 2 points. To eliminate a part of the region, we must generate 2 points within the interval. Now, these 2 points are equidistant from either end. The golden ratio is used to obtain these two trial points within the interval. For purely convenience purpose, we start with an unit interval. So, whatever be the length of the interval, it can be scaled to 0, 1, and we place two trial points a fraction tau from either end, and the tau is the golden ratio 0.618. Note, this point is tau distance away from left end. Similarly, this point is tau distance away from right end, and tau is the golden ratio 0.618. So, this information used to get these two numbers. Now, evaluate the functions at these two trial points. Let us suppose that the right hand side subinterval is eliminated. Let us say this subinterval is eliminated. The remaining subinterval has length tau and it has one old trial point located interior to it at a distance 1 minus tau from the left end point. So, again see how one point is retained from the previous iteration. Each subsequent iteration will eliminate 1 minus tau of the remaining interval. Thus, after n function evaluations, the interval remaining will be tau to the power n minus 1. Let us look at the algorithm. We know that the minimum is bracketed between a and b, set length L equal to b minus a, define a small tolerance value epsilon. Let us first normalize the variable x, so that the x varies from 0 to 1 and the length of the interval is 1 minus 0 equal to 1. So, this can be done by x minus a divided by b minus a. So, we define a new variable w, which is x minus a divided by b minus a and b. So, this can be scaled to 0, 1 by defining w equal to x minus a divided by b minus a. So, we will set a w equal to 0, b w equal to 1 and L w equal to 1, set iteration counter k equal to 1. Now, you get point w 1, which will be a w plus 0.618 L w, and w 2 is b w minus 0.618 L w. You will get 2 points w 1 and w 2. You have to evaluate these points. That means, you have to evaluate the functions at w 1 and w 2. Note that one will be known from previous step. You will use unimodality of function to eliminate a part of the interval, and accordingly you will update the interval. That means, set new a w and b w. If this length of this interval has become very small, less than the tolerance value, we will stop. Otherwise, we set k equal to k plus 1 and go to step 2, where you obtain two new points W 1 and W 2, but one of the points will be retained from the previous step. So, here also effectively we are doing one function evaluation at each iteration. Also note that equal portion is eliminated at each iteration. So, now let us take one example to understand the working. We minimize the function f x equal to 100 minus x whole square, and let us say x lie between 60 to 150. You know that the function attains minimum at x equal to 0, sorry x equal to 100, the minimum function value is 0. We have to first rescale the given interval 60 to 50 to 0 to 1, and this can be done by x minus a by b minus a. So, x minus 60 by 90, w equal to x minus 60 by 90. So, reformulate the problem in terms of w now. So, f of x equal to 100 minus x whole square becomes f of w equal to 40 minus 90 w whole square, where w varies from 0 to 1, and this is the function now we will minimize. So, we will obtain the minimum in terms of w, and again go back to x by making use of w equal to x minus 60 by 90. So, in the iteration 1, we set at w equal to 0, b w equal to 1, initial interval L w equal to b w minus a w equal to 1. So, w 1 we get as a w plus tau into L w, which is 0.618. So, w 1 we get as 0.618, and then w 2 we get as b w minus tau L w, which is 0.382. So, this is 0.382. Note that w 1 is higher. So, I have placed it here, and w 2 is lower than w 1, which is with value 0.382. Evaluate these two functions. F of w 1 is 244, f of w 2 is 31.6. Now, f of w 2, here the function value is lower than the function value here, and w 2 is less than w 1. So, definitely the minimum cannot lie on the right hand side of w 1. So, right hand side of w 1 is eliminated. So, we set a w equal to 0 and b w equal to 6.618. So, the interval from 0 to 1 reduces to 0 to 0.618. Let us go to iteration 2. So, we have interval 0 to 0.618. So, 0.618. So, L w is 0.618 minus 0 equal to 0.618. Again get w 1 and w 2 as a w plus tau into L w. Note that a w, b w and L w has all been updated. So, using a w plus tau L w equal to w 1, I get w 1 as 0.382, and similarly I get w 2 as 0.236. Again evaluate the functions. At w 1 the function is value is 31.6, and at w 2 the function value is 352. Now, w 2 is greater than w 1 and w 2 is less than w 1. So, definitely the minimum cannot lie from a w to w 2. So, we set AW as 0.36 and BW equal to 0.618 in the next iteration. So, if we proceed the same way, at the end of third iteration, you will see AW reduces to 0.382 and BW reduces to 0.618. So, LW is this difference minus 0.236. So, we have now been able to limit W between 0.382 to 0.618, which in terms of x becomes 94.4 and 115.6. So, the minimum has been bracketed between 94.4 and 115.6. We know the true minimum is x equal to 100. So, you have to continue like this for few more iterations to get x close to 0. So, this is how we will solve a problem using golden section search method. With this, we will stop lecture 24 here.